Okay. So today's lecture is about inference in Bayesian networks. So last time we talked for a long time about probability theory, and we did a summary of all the previous probability courses you should have followed. And so we did a recap on that, and then we introduced a way to express a joint probability distribution. And if you remember, what we did was to introduce Bayesian networks, which is a graph structure which allows you to encode a joint probability distribution in a compact fashion by making use of the chain rule first and of conditional independent assumptions to reduce the size of the factors. Okay. So now that we have this structure, what we'll try to do today is to ask questions. So to make queries on this data structure. Okay. And so the problem that we'll consider is called the problem of inference. Okay. And we'll see two types of inference. The first one is a different algorithm to perform exact inference. So algorithms that guarantee that the answer which is provided by the end of the algorithm is the correct answer or the exact answer. And then even though these algorithms are correct, we'll also see that the computational complexity of this algorithm is usually quite bad, typically exponential in the number of variables of the problem. And so the only way then we'll be able to, in practice, make use of this Bayesian network is to resort to approximate inference. So algorithms that are only approximately correct, but much more efficient to give answers. Okay, and so we'll see. I'll mention that there are a few different approaches. That there are different approaches to do approximate inference. In this course, we'll see one of them, which is based on sampling. Okay, but in other courses during your master, you will see other ways to solve the same problem. Okay, so as a recap, first. Let me just remind you what is a Bayesian network. So a Bayesian network is a directed acyclic graph, okay, so in which you have nodes and edges, okay. So this is, for example, the kind of graph which is represented here on the right, where you would have 8 different nodes, okay, and some edges represented by the arrows in purple, okay. Each one of the nodes corresponds to a random variable of your problem. Okay, so in this case, we would have 8 different random variables, x1, x2, x3, and so on to x8. Okay, and then each node xi is annotated with a conditional probability distribution, okay, which is p of xi, given the values of its immediate parents. Okay, so for example, x3, the node here, would be labeled with a conditional probability distribution, which describes p of x3 given the value of its immediate parents, x1 and x2. Okay, and then we have seen that this structure implicitly encodes the full joint distribution, so this guy, as the product of the local distributions that you find at the nodes. Okay. So you will have a product over all n variables, and the factors in this product would correspond to the conditional probability values, so p of xi, given the immediate parents. Also, one thing we spent quite a long time on was about the topology of the Bayesian network. And the thing that you should remember is that the topology is the way that you use to make assumptions about the problem. And in the case of Bayesian networks, the kind of assumptions that we make explicitly are conditional independent assumptions. Okay, so one of the examples that we used was this 5-node Bayesian networks, where we have 2 nodes about at the top, one for a burglar, the other one for an earthquake, and they are related to a third variable, which is whether or not there is an alarm going on in your house, let's say. And then if the alarm rings or not, then there is with some probability either your neighbor John or your neighbor Mary will call you. Okay. So all these 5 variables are related to each other, and the way they are related to each other is described by this structure. Now, given this Bayesian network, what you can do is to evaluate the joint priority of any joint event, so any combination of values of the variables in the problem. Okay. For example, what is the priority that first there is a burglar, but at the same time there is no earthquake, the alarm is going on, your neighbor John is not calling you, but your neighbor Mary is calling you. Okay, and the way you would do that, you would use the Bayesian network to evaluate this joint priority would be simply by going over the nodes, okay, and then reading the value that corresponds to the values that you want to evaluate. Okay, so in this case, you would start at the top, and you would have using the chain rule and this decomposition, that is equal to P of B, okay, because we are asking for B to be true, P of not E, okay, times P of A given the values of the immediate parents, so P and not E, times P of not J given A, times P of M given A. So there is a typo there, it should be, of course, M condition on A. And now, if you replace all these expressions, all these terms by their numerical values, okay, that you can read from the conditional probability tables, you would obtain this product, and from this, you could evaluate the joint probability of this event. Okay, so let's first now talk about exact inference. So inference is basically concerned with the problem of computing some marginal and some conditional probability distribution from a full joint probability distribution. Okay, so typically in the case of simple queries, we would like, for example, to evaluate the conditional probability of some variable given some evidence. Okay, and again, this evidence could concern all the other variables of your problem, or just a subset of these variables. Okay, we could also have a query which is about more than one variable. So for example, here we would have a query about 2 variables, xi and xj, again condition on some evidence E, and inference would be about determining this distribution P of xi and xj given E, which itself you could, using the chain rule, rewrite as the product of a first conditional distribution of P of xi given E, the evidence, times P of xj given xi and E. Okay, and that means if you have an algorithm that you can use to solve simple queries, then you can just extend it immediately to solve conjunctive queries, because you see already here that this product involves 2 factors which are simple queries. Another types of inference that we would like to usually to perform is to retrieve what is the most likely explanation. Okay, so you would not be interested in computing a full probability distribution, but only to determine what is the value, let's say q, for which p of q given E is maximized. Okay, and so this is something we'll see later on, for example, in the case of decoding of speech recognition, where we would have as evidence some piece of sound, piece of audio, and what we would like to determine is what is the text version of that sound, which is the most likely given this sound. And fourth, another type of inference would be the ones that you need to take optimal decisions. So later on we'll see that let's say we have some function v which characterizes the goodness or the utility of some state s prime. What we would like to determine is what is the action A, okay, which will maximize the expected value of this v function. Okay, and this expectation would be over a conditional probability distribution, which is the conditional of p of s prime given s and a. So this typically will emerge in the kind of in the same kind of problem that we've been considering. When you are in a state A and then take some action E, then you would arrive in everything we've seen so far, you would arrive in one state, S prime, but this transition could be stochastic, and in this case you would express the relation between S, A, and S prime as a conditional probability distribution. Okay. Okay, so this, when I mean inference, I mean one of these problems, and usually what will happen is that to solve any of those, we will need to basically determine some, we will need to compute a marginal or conditional probability distribution. Okay, and then once we have this conditional probability distribution, then of course we'll be able, for example, to compute the most likely explanation or to compute the optimal decisions. Okay, so already last week, we have seen one first algorithm to do exact inference, and this algorithm was called inference by enumeration. So I will just go over it again, just to take it slowly today. So what we did in this algorithm is that we started with a full joint distribution over a set of random variables. One of them is q, okay, and q is the query variable. We have then a set of evidence variable from E1 to EK, and then in the joint distribution we have also other variables, but which are not part of the query that we want to make. Okay, and these variables H1 to HR are called hidden variables. Okay, and then typically the query that we would like to make is to compute this distribution at the bottom, P of Q, given some value of the evidence. Okay, and you would like to compute this distribution regardless of the value of the hidden variables. Okay, so you want to marginalize out all of these other variables. Okay, so the way you do that, if you have access to the full joint distribution, would be simply first to select the entries that are consistent with the evidence. Okay, so you select all the rows for which the column of the evidence variable match with the evidence values. Okay, small e1 to small ek. Then you would marginalize out the hidden variables to obtain the joint of the query and the evidence variables. So P of Q and the evidence value is equal to the sum over all the distribution of P of Q and this evidence value over all the possible values for the hidden variables. Okay, so so for each unique combination of Q and the evidence, okay, you would have several other values for the edge variables, okay, and you would just aggregate them all by summing them into a single distribution. Okay. And finally, what you would obtain then is not yet a proper distribution, because the values, the probability values, would not necessarily sum to 1. So you need to normalize the values. Okay, and this is what you do. What you would do simply by first computing some normalization constant z, which correspond to the sum of the values that you've computed at step 2. And then you just divide all the entries, all the values by the z constant, and that then would give you the conditional probability values for PQ given the evidence that you set. Okay, so let's apply, for example, this algorithm to the alarm network of this slide. Okay, and the query that we'll make will be to determine what is the conditional probability distribution of the variable b given some fixed evidence j and m. Okay. So if we do that, we would start first with the joint probability distribution, the full joint probability distribution over all the variables, okay, all the 5 variables. We have 2 hidden variables in our case, the variable e and a, because you don't see them in the query, so we need to marginalize them out. And then if you follow the algorithm, what we need to do is to sum over all possible values of these 2 variables. Okay, so we sum over all combinations of value e and a. Okay, and we would sum what? These distributions. Okay, p of b given some value j and m given from the evidence, and given some value e and a from these 2 sums. Okay, then we obtain some probability tables that we need to normalize, and this is what I write here with this product of 1 over z. In the slide, you may also see that sometimes I I use this symbol, which simply means that that the term here on the right is not yet normalized. Okay, but that I could obtain this term by simply normalizing it. Okay, so more precisely, this symbol just means that the expression on the right is equal to the expression on the left up to some multiplicative and constant factor. Okay, in this case 1 over z. Okay, and so we could compute this, and then we would have access, we would then obtain p of b given j and m. Okay, and these inner terms in the sum, given that we have a Bayesian network, we could compute each of them by simply following the topology and factorizing the joint as the product of the local conditional probability distributions. Okay, so we would have that p of b given j and m is proportional to the marginalization of e and a of the terms that you see here, p of b times p of e times p of a given b and e times p of j given a times p of m given a. Okay. Also notice that sometimes I'm using a bold p, while at some other places I'm not. Okay. This is again because when there is a bold p, what I mean is that I'm defining this factor correspond to a full probability table. Okay. While, for example, here this second factor is not a probability table, it's a single probability value. Okay. So typically, by convention also, every time you see some uppercase letter inside the p function, then it's necessarily then a probability table, while when you only see inside the p function lowercase letters, then that means this factor or this expression corresponds to a single scalar value. Okay. Okay, so we could just apply this and we would obtain a correct result. But if you were to implement this algorithm in Python, let's say, then you would quickly realize that this algorithm, inference by enumeration, is slow because you need to compute the full joint before marginalizing the hidden variables. Okay. So that means you would start with small tables, small conditional probability tables, but very quickly, because of what you do in the inner sum, you would have to compute a very large table, which is typically whose size is typically exponential in the number of variables, before removing the hidden variables. Okay, so you would have this intermediate step, which is very costly because it's exponential in the number of variables. So of course, this is not something we'd like to have if you want to be efficient. So what you could notice is that the factors that do not depend on the variables in the summations can actually be factored out. Okay, you can just pull them over to the left, which means that the marginalization step does not have to be done at the end. Okay, so what we had was that the conditional of b given j and m is equal to this expression, okay? But we could just pull out, for example, p of b out of the two sums, because p of b does not depend on e and a, okay? And the same for p of e, it does not depend on a, so we could just pull it out of the first sum. Okay, and if you do that, you would obtain now this expression. And now if you were to implement this second expression in a computer program, you would not have to build the full joint joint probability distribution. Okay, you would only have to build the largest table you would have to build typically would correspond to this inner sum. Okay, where we would have, so I don't know how many there are, but you see that we'll not have to build the entire joint distribution. Okay, we would build this one, then we would get a new distribution, and then we would then make the product between this intermediate distribution and p of e. We would get a new intermediate distribution, and then we would multiply it again with p of b. So more formally, in terms of pseudocode, this algorithm, which is known as, it's still inference by enumeration, but just rewritten in a smarter way, would go like this. So what we want to do, so we would start with some Bayesian network, which represent our joint distribution. And then we want to make the query p of x given e. Okay, so I'm sorry for the changes of notation, but you should simply understand that x corresponds to our previous variable q, and this variable y corresponds to our previous variables h. Okay, but other than that, it's the same. Okay, so x, the query variables. Then we have also some observed values for the evidence, okay, that correspond to all the variables e. Then we would initialize the distribution over x, which initially would be empty. Okay, so typically q of x would be some table which a certain number of rows, depending on how many values the x variable can take, and you would initialize the corresponding probability values to 0. Okay. Then for each unique value xi of x, what you would do is that you would like to compute p of xi given e. Okay, and to do that, you would use a second algorithm which is called enumerate all. Okay, which is the function defined below. Okay, and this function would take as argument a set of variables and some evidence. So the set of variables in our case would be all the variables from the Bayesian networks, and the evidence would be, in this case, the union between the values e, lowercase e, and the value xi for which we want to compute the conditional probability value. Okay. Then you would repeat that for all unique value xi. You would then fill in all your table, and finally you would normalize the entries. Okay. Then this function enumerate them all would be basically an implementation of this trick. So you would maintain a list of variables and the evidence values, and this function would return a real number. Okay. So first, if the list of variables that you pass to the function is empty, then you just simply return 1. Otherwise, you pop out the first variable from this list. Okay, let's say this variable is some variable y. If y has a value in the evidence, okay, then what you do is that you return p of y given the value of the parents, okay, times the value, the probability values of the remaining variables for the same evidence. And so you would call recursively that same function, but now not on the original list of variables, in the same list, but in which you have removed the variable y. Okay. If, on the other hand, y is not part of the evidence, that means y is a hidden variable, then you need to marginalize it out. Okay, and the way you would do that would be simply by summing over all the values of y. Okay, you would sum all the probability values of y given its parents. You would obtain some value. And then for each of them, of course, you would also need to enumerate, to make this recursive call to the enumerate function, where you would pass as the list of variables the remaining variables. And as evidence, you would pass the same evidence values, except that you would extend it with the value y that you are currently considering in the sum. Okay. So, for example, if you look at this term, okay, we would have that E is not part of the evidence, in this case, because you have only two evidence variables, J and M, okay. So we would be in the second, in this case, for the if statement. So we would have, to compute all, to return the sum over all values E of the variable E of P of E given the parents. In this case, E has no parents, okay? And then for each value E, you would call recursively this enumerate all function, where we have passed as variables the remaining variables in the ordering. So in this case, we would pass the variable A, J, and M, and the evidence vector would be J, M, and the current value E. Okay, and this recursive call would then return this part of the expression. Okay. So the complexity of this algorithm, so what you can basically understand is that this algorithm would build some kind of tree, and which would be traversed in a way which is identical to what you would do with depth first search. Okay, so the complexity would then be the same, which is linear with m, the number of variables, and exponential with the number of variables. Okay, where d is the size of the domain of the variables. Okay, so how many unique values the variables can take. So this tree, for example, you could draw it, and for the case of PB given J and M, we would obtain this. Okay, so we would start with P of B, which is at the top. So yeah, by the way, this is an important point. When we pass this list of variables, okay, we need to pass them in some ordering. Okay, and this ordering, we'll see, is quite important. But so if we say that the ordering is first B, then E, then A, then J, then M, then we would obtain this tree for this query. Okay, and so what we would do is that we would compute first P of B, and then recursively call this function on all the values of the evidence uppercase E. Okay, so you would multiply P of by P of E and then P of not E. And then for each of these values, we would also call recursively the function, which would then compute P of A given B and E first, then P of not A given B and B, and the same for the other part of the tree, where we would compute P of A given B and not E, and P of not E given B and not E. Okay, and then we would proceed recursively like this. So if you look closely, that's better than just computing the entire joint distribution first. Okay, but this is still quite inefficient actually, because, for example, these two branches there, and so this one and this one, are actually identical. And the same for this branch with this branch, they are the same. So that means there are parts of the tree that we could, if we were just following this algorithm, that maybe we would recompute several times. And that's something we'd like to avoid. Okay. And so the way we could avoid that would be by storing intermediate results and then checking if we've already computed this result before computing them. Okay. So the algorithm then that we would obtain if we implement this idea is known as inference by variable elimination. And so based on the idea that we'll carry out the sums from the right to the left instead of doing this in the opposite direction from the left to the right, and we'll store intermediate results that we'll call factors to avoid recomputations. Okay, so we'll interleave two steps, joining tables and then eliminating hidden variables. Okay, so basically if we go back to this expression, what we would do, instead of computing this expression from the left to the right, we would compute it from the right to the left. And so we would start with this inner probability distribution. We would compute it once, okay? And once we've computed it, then we would multiply it by P of E, and then we would multiply it again with P of B, okay? So let's see how it would work on the same query again. So we have that the conditional P of B given J and M is proportional to the join of P of B and J and M, which, by following the structure of the Bayesian network, is this expression that you've seen a few times already today. And so what I will do now is to rewrite these probability values in terms of factors, okay, which would be these intermediate results. So the factors, I would have a first factor f of f1, which would depend on B. Then I would have a second factor f2, which would correspond to scalar values for E. Then I would have a third factor, which would depend on A, B, and E. Then a fourth, which would depend on A, and then a fifth, which would depend on A. Okay. And so what we would do is that we would have this expression, then we would decide the variables that we want to remove. Okay, and we could say, okay, I want to eliminate the variable A. And so the way you do that would be to identify all the factors in which this variable appears. Okay, so in this case we would have F3, F4, and F5 because A is an argument of this factor. We would combine them all together and by doing so, we would marginalize out the variable a. Okay, and so after this computation, so we'll say we'll sum out a, we would be left now with a new factor, a new intermediate result, a new intermediate probability distribution, which we call f6, which now would no longer depend on a. Okay, and it would only depend on the variables that are left among the factors that we have joined. So in this case, the variables that are left are b and e. Okay, then we would do this again. Would sum out the next hidden variable. In this case, there would be only one left, which is the variable e. So we would combine f2 and f6 together into a new factor f7, which depends on b. And then finally, we would have two factors f1 and f7, which we would recombine again into a last factor f of f8, let's say, which then would allow us to compute this joint probability distribution. So more specifically, each factor fi, we should view that as some multidimensional array, okay, or some kind of tensor, which is indexed by the values of its argument variables. Okay, so for example, we had f4, okay, this one, which is a tensor, okay, or an array, where you have as many entries in this array as you have combinations of the values of the arguments. So in this case, you have only one variable as argument, okay, and so we would have simply as number of entries the number of unique values of a, okay, and then the actual values that you put are correspond to this, for example, to the part of the conditional probability table associated with the values of the argument. Okay, so in this case, we would have first p of j given a, and second p of j given not a. Okay, and that would be the values that we put in this tensor. Okay, in this factor. Okay. Again, you should not interpret these factors as a probability distribution. Okay, because you see these values, they are not summing to 1. Okay, and it would not make sense to normalize this, okay, because they are about different things. The first entry is about the condition of j given a, okay, while the second is about the condition of j given not a. Okay. Then when I write this factor with an uppercase letter, I always mean a tensor or some kind of array. If I put as argument a lowercase letter, then I mean that I want to access some particular value in this tensor. Okay. So for example, f4 of lowercase a would be that I want to access the entry in this factor which corresponds to the positive value for a. Okay, which is this one, and the same for the opposite value, not a, would correspond to this entry. And I'm sorry, I see there is a typo. These two values should be the same. Okay. Then what we'll do at the beginning of this variable elimination algorithm would be to set the factors to initialize them all with the conditional probability tables that are annotating the nodes of the network. Okay, and you would take these conditional probability tables, and of course you would condition them on the evidence that you care about. Okay. So these are the factors. Now we have to define what we mean exactly when we say that we are joining several factors together. Okay. So I will define for that a new operator, which I will call the pointwise product that I will denote with this cross, or simply a join, okay, of two factors f1 and f2, and this operation will yield a new third factor, which let's say is called f3. So if you've already followed some courses on databases, then it's basically the same as a joint in a database. Okay. So the variables of the factors f3 correspond to the union of the variables in the two factors f1 and f2, and the elements of this factor f3 are given by the product of the corresponding elements in f1 and f2. Okay. So as an example, let's say we have a first factor that depends on two variables a and b, and then a second factor which depends on the variables b and c. Okay, we would have these numerical values for f1 and this other for f2. If now we compute this product of f1 with f2, we would obtain a new factor f3 whose variables are given by the unions of the variables in the two factors f1 and f2. So that union is a, b, and c. And then the elements, so we would have 8 combinations now, if all the variables are Boolean variables. And each entry would correspond to the product, which would be given by the product of the corresponding elements. Okay, so let's say with this first one. So this entry corresponds to A being positive, B positive, and C positive. Okay, and so we would just look for the A and B being positive in F1, so 0.3, and then B and C being positive in the second factor. We would have these two values, 0.3 and 0.2. We would multiply them together and we would obtain 0.06. Okay, let's pick this other one. Let's say A negative, B positive, and C positive. Okay, so we would look for this combination of values in the first factor. Okay, it would be this one, so 0.9, and then positive positive would be this entry, 0.2, so we would have 0.9 times 0.2 equal 0.18. Okay, and so you would repeat that and you would obtain at the end the factor f3, which depends on A, B, and C. Okay, and so again you see that when you combine several factors together, the size of this factor will be larger. Okay, and so we started with two factors of size 4, and now we are left with a third factor of size 8. Okay, so this is for the join, and then the second step is about eliminating or summing out a variable from a factor, which would be simply done now by adding up the subarrays that are formed by fixing the variable to each of its value. Okay, so if we start with the factor f3, which we have just computed, and we want to sum out one of the variable, let's say the variable a, then we would just select all the subarrays that we obtain when we set a value for the variable that you want to sum out. So in this case, with two values for a, positive and negative. Okay, and we just extract the subarray for each one of these two values. We would obtain this factor and then this factor. Okay, each of them would be of size 4, and they would correspond to this upper part and then this lower part of the table. And then we just sum these subarrays together into a new factor, which now would only depend on the variables that are left, so B and C. Okay, and so we would obtain, for example, these values now. So now that we have defined these two operations, join joining and eliminating, we can go back to the original query and define the variable elimination algorithm as follows. So let's say we want to compute the conditional, so P of Q given some evidence E1 to EK. Okay, so what we would do is that we would start with the factors, we would initialize the factors with the local CPTs, the local conditional probability tables that we can just obtain from the Bayesian network. Okay, and we would instantiate these tables with the evidence that we set in the query. Okay, and then what we would do is that we would have a loop, which is the second step, in which you would go over the hidden variables one by one in some ordering that you have to decide. And then at each iteration, you would pick one of these hidden variables, let's say h, and then you would join. So you would maintain the list of all the factors that you have, and then you would identify all the factors that mention this variable h, and then you would join them all together. Okay, so you would apply this join operation in between all the factors in which h appears. Okay, and then since h is a hidden variable, you want to marginalize it out, so you want to eliminate it, and this is what you would do on the factor that results from the previous step. Okay, so this is exactly what we did there when we sum out the variable a from the factor that we just obtained from the join. Okay, so you would repeat that until you no longer have any hidden variables. Okay, and once that's the case, then you are left with a usually short list of factors. You join them all together, and finally you normalize them to obtain the condition of Q given the evidence. So this is something I think you will practice with Antoine during the exercise sessions. It's not very complicated. If you just follow this recipe and you do it once or twice, then you will see it's quite easy. So there is a question in the chat which says, how come when adding f(a) of b and c and f of not a and b and c, we don't get the same value as in the table before for f, b and c? Because these factors, they do not, so that's a good question. So the question is, why this f2 factor in which you only have b and c has not the same value as this one that you obtain here? Okay, so the reason is that they don't correspond to the same object at all. How to explain this? It's a good question. I'm just thinking how to explain that. But I think probably the best to understand that is that even though the arguments do not define probability distribution that could correspond to so the factors are not necessarily about joint probability distribution of their arguments. Okay, and so this is something, for example, that you see here. Okay, you have two different factors, f4 and f5. They both only depend on the variable a, okay, but they are not about the same probability distributions. Okay, one is related to p of j given a, while the other is related to p of m given a. Okay, so already there you had two different factors with the same arguments. Okay, but the values inside these two factors are not about the same conditional probability distributions. Okay, and it's this, and we have, for the same reason, that's why f2 and and this one are not equivalent. Okay. So this is the algorithm, the general algorithm, and if you apply it, then it's already much better than the naive algorithm that we had from the start at the start of this lecture. If you pay even closer, so there is another trick that you could use, okay, which is a property which is known as relevance. So if you consider another query, let's say p of j given b, then this thing, by just following the topology of the Bayesian network, is proportional to this expression, okay? And in this expression, what you see is this last factor, which is summing over the values of m, the probability of the probability values pm given a, okay? And so here we would marginalize the only variables on the left of the conditioning, and so since p of m is a proper probability distribution, if you marginalize this distribution, you would obtain just 1, the scalar value 1. Okay, so this term, without doing anything, I know that it's equal to 1. Okay, so that means it's actually irrelevant for the query, and we would not need to have it at all. So another way to say the same thing is that we would obtain the same result if we had removed the variable m from the network. Okay, and so if you do that, then of course you would reduce the size of the factors that you have to compute through the algorithm, since you have fewer variables because you've removed some of them. Okay, and so this is something you can always do, and so if your query is p of q given e, then you can remove all the variable h that are irrelevant for the query. And this is something you can check. You can say that, you can prove that h, some variable h, is irrelevant for the query q given e, unless h is one of the ancestors of the variables in the union of q and e. So in this case, the union of q and e for j and b. So j and b are the two variables in the query. Their ancestors, okay, are this set j, a, e, and b. Okay, and so you see that in this set of ancestors of the variables, m is not part of it. Okay, and therefore m is irrelevant, and you could remove it before applying the algorithm. Okay, so this is nice, but let's reason a bit about the complexity of this algorithm. Okay, and for this, let's consider this scenario where we would have a single variable z at the top, at the root of our Bayesian network. And then this variable z would be connected to n x variables, x1, x2 to xn, and each of them would be connected to another variable, yi, y2 to yn. Okay, and let's say the query that we would like to perform is to compute the conditional probability distribution of this variable xn, given some observed value, some evidence values for all the y variables. Okay, and so by doing so, what we would have to do at some point is to marginalize out the z variable and all the other x variables from x1 to xn minus 1. Okay, and so we could just apply this variable elimination algorithm, but when we have to apply it, we have to decide in which ordering we are picking the hidden variables. Okay, and so there are many different orderings, but it's interesting to first evaluate what would happen if we first eliminate z and then x1 to to xn minus 1, or if we first remove or eliminate the x variables and then finally the z variable. So in terms of complexity, the two orderings would be quite different, because if you first remove the z variable, okay, what would happen is that you have to join all the factors in which z appears, okay? And the factors in which z appears would be factors that are associated to the x nodes, okay, and of course the z nodes, okay? So z would appear into n-1 x factors, and of course with the z factor. So it would appear in n different factors. So if we start the algorithm by first eliminating z, we would join together n different factors, okay, and the resulting factor would have a size which is exponential in the number of variables that appear in this union of factors. Okay, so in this case it would be exponential with n-1, and that's maybe not a good idea. On the other hand, if now this factor is not exponential to up to n-1, it's actually exponential with n+1, sorry, because we also have to add the xn variable and the z when we compute the join, okay? So we are joining n+1 variables, and therefore the size of this factor would be exponential with n+1. We could have done the other way. We could have eliminated first the x variables and then z, and if we do that, every time you actually remove, for example, one of the x variables, okay, the x variable only appear, for example, in the factor associated to the y, okay, but this one is not a factor because it would be insociated by the evidence, okay, so we would just remove this thing directly. And by doing so, you never have to build a very large factor, which is exponential in the size of the variables, of the set of variables. Okay, we can show that in this case it will be proportional to only 2 to the power of 2 if we assume Boolean values for all these variables. So what we have just shown is that the computational and space complexity of variable elimination is basically determined by the largest factor that you need to compute when you perform this algorithm. Okay, and this largest factor depends basically on the ordering that you use. Okay, and unfortunately we can show that it's not possible to find an ordering in which you are guaranteed to only have small factors. Okay, there is no single algorithm that will guarantee you that for any Bayesian network that you provide to the algorithm. So you can try to do your best and let's say have some greedy heuristic instead, which would be to eliminate whichever variable will minimize the size of the resulting factor. Okay, and in this way would hope that you would always maintain a small size of factors. There is also one special case which arises when the Bayesian networks is a singly connected network or a polytree, which is a kind of network in which any two nodes are connected by at most one undirected path. Okay. So if you just remove the arrows and just consider links between nodes, if there is no cycle, that means there is just any two nodes are connected by at most one path, then you have a singly connected network. Okay. And for this network, you can show that time and space complexity of this algorithm would be only linear in n, the number of variables, and exponential only in the largest number of parents which is k, that a parent can have, that a variable can have. Okay, which is better. Okay, but of course, for this to be true, that means that you need to be able to encode the joint probability distribution in this way, and that may not always be possible because you would have to make usually very strong conditional independence assumptions. Okay. Okay, and then finally, so if we had done the optional lecture 2b on constraint satisfaction problem, I would have told you about a bit of logic and a problem which is known as the satisfaction problem, and which is a problem which is about, let's say you are given some Boolean expression like this, where the U letters correspond to Boolean values or Boolean variables. This symbol means the OR operator, and this other one means the AND operator. And the question is there a combination of the U values? Okay. Is there an assignment of the U values such that this expression can be evaluated as true? Okay. And so this is known as the satisfiability problem, not the satisfaction problem, sorry. And so this problem is fundamentally difficult, and it's known to be NP hard or NP complete. And that means today we don't know any algorithm which can solve this kind of problem efficiently. Okay. And so in terms of, so why am I talking about that? Because inference, as we have expressed it, can be reduced as a constraint satisfiability problem. The name of this problem is called TreeSat, but it's not important for you to know. And so that means by reduction, inference is actually as difficult as this satisfiability problem. Therefore, it's also NP complete. Okay. So inference in Bayesian network is also NP complete, and that means, so whatever trick we try to add into our procedure, it can be proven mathematically that there is no known algorithm which would be efficient. Okay. Okay. At least until today, we don't have a solution for that. Okay. So in other words, and this is a very strong result, if you really want to do exact inference, so to compute some probability distribution of Q given some evidence, you will never be able to write a generic algorithm which will be efficient. Okay? And by efficient, I mean better than exponential in the number of variables. So this is bad, and this is why we have to resort to approximate inference algorithm, because we do know that there is we'll never be able to find a single algorithm that will be efficient in all cases. So let's just assume then that that's fine. We'll be happy even if we can only find an approximate solution to our query. Okay. So this is the goal of the second family of algorithms that we'll see today, which are known as approximate inference algorithms. I think it's a good time now to take a break. So it's 10 past 8. We can resume in, let's say, 10 minutes. So 1020. All right, so we'll resume. So what we did so far was to consider inference problems, which is about basically computing some conditional probability distribution given some evidence with or without other variables that you would like to marginalize out. And we have seen basically two algorithms so far. The first one is inference by enumeration, and then the second one is variable elimination. Both of them are exact inference algorithm in the sense that they will give you the exact answer, the exact probability distribution values. However, what we've seen is that their complexity in the worst case is always exponential in the number of variables in the problem. Okay, so for most interesting and real-world problem, these algorithms are basically impractical, and we'll have to resort to approximate inference. So algorithms that will only give us an approximate answer, which will make it better and better if we have some computational budget, but the solution will always be approximate. But it will be much more efficient to compute and to obtain this answer. Okay. So as I said, as I just said, exact inference is intractable for most probabilistic model of interest, and this would happen, for example, as soon as you have many variables, because if the complexity grows with the exponentially with the number of variables, as soon as you add variables, then you are basically making the problem, the inference problem, even more complicated. It's also usually intractable when you have continuous variables. So in everything we have said so far, we assume that the variables were discrete. Okay, and so but for most interesting problems, the variables would be continuous. Okay, so you could say, okay, I would just then assume that I will discretize the space of value of my continuous variables into a discrete and finite set of values. You could do that, but then typically you'd be left with a huge number of unique values. Okay, and that would not help. That would not make the algorithm so much more efficient, because the complexity of this inference algorithm is, let's take this slide here. So we have the complexity with exponential in number of variables. Okay, but the d corresponds to the number of unique values, so to the size of the domain. So if you discretize a continuous space, d usually will be a quite large value, and powers of a quite large value is usually huge and very quickly, and so you will not be able to run these algorithms on continuous values as well. Okay. You may also have other problems like undirected cycles and other things. So as an example of this, this is what you see in the slide, is some ongoing work that we are doing with one of my PhD students. Is trying to control a robotic arm that you see here on the left, and this upper part is the robotic arm. And what he wants to do is to control the grip, some kind of gripper, which is some kind of end at the end of the arm, in order to grasp some object which would be located, let's say, on a table. Okay. So what we did in this work was to formalize the problem in terms of a probabilistic graphical model. So Bayesian network as the one that you see here on the left, on the right, sorry, where you have 5 variables or sets of variables. You have P, which is about the location of the object in XY space on the table. we have the object itself. So in this case, the object is a mug, but it could be a bottle, it could be a box, it could be other things. Then you have the position h of the hand around relative to the object itself. Okay, so the hand could be, for example, above the object, but it could be next to it with some angle and so on. Okay, and then we have two other variables. I is the image that you would capture, for example, with a camera. And so in this case, we are using a Kinect, which is a depth camera, which is producing this kind of image that you see here on the top right. And finally, we have a fifth variable, which is S, which is about the success, which is what if the robot starts some grasping procedure in some position H, starting from some position H on some object O, okay? Does it lead to a success, to a successful grasp? Okay. So this is a very simple way to model the problem, and you see that this Bayesian network can be used to solve real-world problems. But we would not be able to use an exact inference algorithm to solve inference queries. So typically, the inference query that we would be interested in our case would be to determine P of H. What is the relative position that I should use, given that I observe some image I, and that I want the grasp to be successful. So in this case, we would have P of H, given S being positive, and given some image. Okay, and O and PO would be variables that we would not observe. Okay, they are hidden. But still, we want to, and so in the query, we would like to marginalize them out. Okay, and so of course, this would be quite difficult. First, because I is a variable about images. Okay, so it would be already impossible to write down explicitly a conditional probability table for this variable given O and P. Because the space, just the domain of all the images, is so big that there is no way we could write this table explicitly. And so, but what we have instead is a simulator which, given some object and some position, can simulate the images that we would obtain from the camera. Okay, so at least we can sample from the conditional Pi given O and P. Okay, and in the same way, we don't know explicitly the table for P of X given H and O. Okay, but we can simulate it. Okay, given some position of the robot gripper H for some object O. Okay, we can simulate whether or not the grasp would be successful, and so this is what would be encoded. So the kind of conditional probability table in this Bayesian network would be encoded as simulators, basically. Okay, but so my point is just to say that these two algorithms that we've seen, you could not apply them on this problem, even though this problem is not that complicated. It's just 5 variables, and that's it. And the structure also is not that complicated. So the solution, is to really abandon exact inference and instead to develop approximate but faster inference algorithm. So we'll see a family of methods today, which are about sampling methods. And so what we'll do is that we'll try to produce answers simply by repeatedly generating random numbers from some distribution of interest. By simply sampling from some distribution, we'll be able to derive, to approximate the query that we want to target. There are other methods or other family of methods, and I will just mention them for your information. We have, for example, variational methods which formulate the inference problem as some optimization problem, assuming usually a variational family. Then you have belief propagation methods which formulates inference as a message passing algorithm. I think you will see some of this algorithm in a later course about information theory. And then you could also use machine learning methods to learn an approximation of the target distribution by using training examples. Okay, and this is something you'll see also in later courses, and that I will also mention again when we talk about learning in a few lectures from now. But so let's cover today the sampling methods. So the basic idea would be that we have some sampling distribution that I will call S, okay, and that I will use and from which I will draw n different samples, okay. And then from these samples, I will try to compute an approximate posterior probability p hat, okay. So every time you will see a hat above some symbol, that means I'm making an approximation of the symbol, okay. So in this case, I'm making an approximation of the probability distribution, P. And of course, for this sampling method to be useful, we would like them to have some properties of convergence, and meaning that as you increase the number of n of samples that you draw from S, the estimator will be consistent, meaning that it will tend to the true value that you want to approximate. So this is the motivation behind this family of methods, behind sampling algorithm, is that comes from the fact that generating samples is often much faster than trying to compute the right answer, okay, as you would do, for example, with variable elimination. Because you just have to draw random numbers, and that's usually very fast. You don't have to go through some factors whose size is exponential in the number of unique values. And so in this second part of the lecture, you will see these cartoons where basically we will try to reason about the probability distribution of shapes like circles, squares, and triangles, and colors, blue, red, and green. Okay, and we'll just assume that we have some kind of machine that we can use to sample from this joint distribution. Okay, and that means if we can sample sufficiently many times, then you can just fill in some box where we have as many boxes, sub-boxes in this box as we have combinations or unique values from the joint. So in this case, it would be a combination of a shape and a color. And then we just fill in all these bins by the number of times we have generated such combination. Okay, so this is just basically a cartoon representation of a histogram where the sub-boxes are just bins from this histogram. Okay, and we would fill the bins using the samples that you generate. Okay. So the first thing that we'll need to have is some way to sample from the distribution of some discrete variable x. Okay, so let's just first assume that we have just a single variable x which is discrete, and we know the probability distribution for this variable. Okay, so an algorithm that you could use to generate samples from this probability distribution would be to assume that, okay, this is a discrete variable and I have only up to k different outcomes, x1 to xk, okay, and each of them comes with a probability p of xi, okay. Then the second assumption will be that we have a way to sample from some uniform distribution, okay, that I will denote by u between 0 and 1, okay. So typically, if you are just using a standard programming language, you will have access to some ran function, which when you call it, returns some number from 0 and 1, okay? And if you call it again, you would get another sample. If you call it a third time, you get another value, and so on and so on. And the distribution of all these values would be uniform between 0 and 1, okay? Now, given that we can do that, the idea is quite simple. You would start with the 0, 1 interval, and you would divide it into k different regions, k different segments, one for each of the possible outcomes, okay? And each region would have a size which is given by the probability of that value, okay? So P of xi, okay? So for example, here we would have 1, 2, 3, 4, 5 different values for x, and the size of each segment is equal to P of xi, okay? So this value in gray is much more likely than the others, for example. And this is why the size of this bin is larger than the others. Okay. And now to actually sample from the distribution, what we would just do is that we would sample some number u from the uniform using this run function, and then we would return the value associated to the region in which u falls. Okay. So for example, if u is around, I don't know, 0.1, then it would arrive here, and so you would arrive in this bin, and you would return as value the value x1. If on the other hand the u value that you draw is equal, let's say, to 0.9, then you would arrive in this bin, and you would return as value the last xk value. Okay. So this is another example of the same algorithm where we would start with a distribution PC over a discrete variable C, which can take up to 3 values, red, green, and blue, and for each one of them we know their probability, so 0.6 for red, 0.1 for green, and 0.3 for blue. Okay. And now if we draw a random number between 0 and 1, if this random number is between 0 and 0.6, then we just generate a red sample. If it's in between 0.6 and 0.7, we generate a green sample. And if it's above 0.7, we generate a blue sample. Okay? So this is nice because given this procedure, now we can implement prior sampling, which is a procedure to sample from a Bayesian network, okay? In which for now, we would not have any observed evidence. Okay, and the idea goes as follows: we would go over the variables, the nodes of the Bayesian network in topological order. Okay, and we would sample each variable in turn. Then, so we would sample this variable using this procedure, because at each node, what you have is a probability distribution over only one variable, okay, the variable associated to the node, okay? And of course, the probability distribution from which you sample is conditioned on the values already assigned to the variable parents. Okay, so let's come back to this sampling procedure where we would like to samples from our distribution of objects of some shapes and some color. Okay, so we could say that we have a Bayesian network with only 2 nodes. The first node would be the shape, and then the second would be the color given the shape. Okay, so you could imagine that this part is drawing from the distribution of shapes, and then this robot there is drawing from the conditional distribution of colors given shape. Okay, and then at the end you would produce sample with this prior sampling algorithm that you would fill into the bins of this box. Okay, and these samples then would follow the distribution of the joint. Okay, so in terms of pseudocode, it's quite simple. So we would initialize some empty vectors with n elements for n number of variables, and then for each of the variables in the Bayesian network, okay, we would set in position I of the vector the value returned by a random sample drawn from the conditional, the local conditional probability distribution of the node. So P of xi given the value of the parents. Okay, and then we would return a single sample. So, for example, we could have this situation where we have this Bayesian network over 4 variables. So we would have a variable about whether or not there are clouds today, then whether or not we are turning on some sprinkler. Okay, let's say it's summer and we don't want the grass to dry out. We would have a third variable about the rain, and then a fourth variable about the grass being wet or not. Okay, so we could say we describe this problem using this particular Bayesian network, using this topology. Okay, and so at each node you would have these conditional probability tables. Okay, so if then we run important sampling, prior sampling, we would loop over the nodes in topological order. Okay, so we would start at one of the roots. Let's say, so in this case we only have one of them, which is the cloudy variable. We draw a value from the local probability distribution PC. Okay, and the random sample that you obtain is a positive sample. Okay, so when it's green, it means that it's positive. Okay, and we would assume that all the variables here are Boolean variables. Then we would go over the next variables in the ordering. So we would have sprinkler and rain. Okay, and so now we would draw value from the conditional, for example, from the conditional P of S, given that C is positive. Okay, so you need to draw from this probability distribution. Okay, and the same in the right part, where we would draw a random sample from PR given C. Okay, where C is positive. So we do this for the sprinkler variable. We would obtain a negative value for the sprinkler variable, and we do that for the other one, and we would obtain, let's say, a positive value for the rain variable. Now, given that the parents sprinkler and rain are negative and positive, that means when we have then to sample from for the wet grass variable, the W variable, we would have to sample from this probability distribution, and which we would do, and then let's say obtain some positive value. Okay, so we could repeat this process over and over, and at the end what we would have is that we would have collected a bunch of samples from the Bayesian network. Okay, and now if, let's say, we want to know what is the marginal distribution of the W variable. Okay, so this is our query. We don't have any evidence, and we want to marginalize out all the variables but the W variable. Okay, so you could use these samples that you obtain with this prior sampling algorithm. Okay, and you could just use the counts. So how many times do you obtain a positive value for W, and how many times you obtain a negative value? Okay, so in this case, for the positive, among these 5, there are 4 of them which are positive, and 1 of them which is negative. Okay, now you would have these counts. If you normalize them, then what you would obtain is an approximation of the marginal distribution P of W. Okay, and as you draw more and more samples from this from your Bayesian networks, then the P hat of W will become closer and closer to the true distribution P of W. Okay, and you see that never, when we run this algorithm, we had to build some join of factors, whatever. We just have to traverse the Bayesian networks as many times as we want to generate samples, and usually that will be much smaller than some exponential number. Okay, but how can I guarantee that this P hat of W will actually become closer and closer to the true distribution? So for each of the algorithms that we'll see, we'll try to analyze a bit the result, the kind of answer they give us. So for this prior sampling algorithm, the priority the priority values that it generates for a particular event. The priority that prior sampling generates a particular event, okay, is given by the sampling probability that we are using. Okay, so remember when I first defined this procedure, okay, I said that I would be starting from some sampling distribution S. Okay, so the sampling distribution S is simply, in our case, given by the fact that we follow the Bayesian network structure, and then for each of the nodes we draw from the local conditional probability distribution given the parent values. Okay, and at the end we just so all these probability values are multiplied together, and this expression is nothing else than the joint probability distribution P of x1 to xn. Okay, because we do know that Bayesian networks encode properly the joint distribution in this way. Okay, so this factorization is correct by construction. Now let n, okay, of some combination of values x1 to xn denote the number of samples for this event. Okay, then we define the probability estimator p hat of x1 to xn simply as the number of times we have drawn this event over the total number n that we've drawn. Total number of n of events that we've drawn. Okay. Then as n, the number of samples that we draw, tends to infinity, okay, if we replace p hat by the way we by this expression n over xi to xn over n, then this thing will tend to the sampling distribution. The sampling probability, will tend to the sampling probability, which is s of x1 to xn. Okay, and this, by construction of the Bayesian network, is equal to the joint probability of the event. Okay, and that means prior sampling is consistent. Okay, as you just dedicate a larger computational budget, so as you increase n, you will get better and better answer. Okay. So this is fine as long as we do not have any evidence. But now let's assume that we want to build some estimate p hat of x given some evidence e. Okay. So what we could do is simply to reuse the same procedure, but just throw out all the samples which do not agree with the evidence. Okay. So again, we would have the same procedure. So we would draw from the Bayesian network by following its topology. So let's say first we draw a shape, and then we draw a color given this shape. Okay. Now, if let's say we want to condition on the color blue. Okay. So that means we just throw out, we just discard all the samples which are not blue. Okay. And this is what this third robot would be doing. Everything which is blue it would be put into one of the bins, okay, but everything else would just be discarded, okay. And at the end, what we would then obtain is the conditional probability of the shape given that the color is blue, okay, which is which is this approximation p hat of x given e, okay, p hat of shape given blue, basically. So this algorithm is known as rejection sampling. So it's very easy to express in terms of pseudocode. So again, you have some budget n, number of samples that you would draw, and then at each iteration, you would use the prior sampling algorithms that you've seen before to generate some sample x. If this sample x is consistent with the evidence, then you just add the sample to your bins, okay? And so n would be a vector of counts for each value of x, okay? and so you would increment by 1 the counter into the bin associated with this value. Okay. And then you would repeat that for n iterations. At the end, you would get a certain number of counts for each value lowercase x of the variable x, and that you normalize then to obtain an approximation of the conditional px given e. Again, we can show that this algorithm makes sense. Okay, so if you consider the posterior probability estimator p hat of x given e that we obtain by rejection sampling, what we have is that there are a certain number ne of samples that you have generated for which the evidence is satisfied. Okay, and among those there are a certain number n of xne that correspond to the joint values x and e. Okay, the query and the evidence. Now this numerator and denominator you can both divide. You can divide them both. Sorry, you can divide them both by n. Okay, the total number of samples that you draw. Okay, and as n will tend to infinity, the numerator then will approximate the joint p of x and e, and the numerator will approximate the joint p of x and e, and the denominator will approximate the marginal pe. Okay, and this is just the definition of a conditional probability. Okay, so p, so that's why this estimator p hat of xe as n tends to infinity will tend to the probability values that we wanted to compute. Okay, so therefore rejection sampling again is consistent. So this is out of the scope of this course, but you can also show that the standard deviation of the error in each probability is proportional to 1 over the square root of n, where n is the number of samples used to compute the estimate. So meaning the number of samples in the bin that arrives for this particular combination of values. Okay, so this is nice, but there is still a huge problem, which is that many samples may be rejected. Okay, and this would happen if the evidence on which you will be conditioning on is unlikely. Okay, because there would be very few sample x, very few samples that would match with the evidence. Okay, so if you go back to this cartoon, if the evidence is very rare, very unlikely, then almost everything will be discarded. Okay, and we'll only keep a very few portion of events to actually compute our estimates. Okay, so in this case, this algorithm would be very inefficient. Okay, so then to improve over that, what you could do is to just not wait for the generation of an event which matches with the evidence, but to directly force the value of the evidence. Okay, so to clamp the evidence variable to the evidence value. Okay, and then to sample the rest. Okay, so let's say again we want to compute the marginal of the shape given blue. Okay, so instead of drawing, so what we could do is to draw a shape, and then instead of drawing a color, we'll just force this color to be blue for all shapes that we have drawn. Okay, and then we would put all the samples in our bins. So that would be much more efficient, but you have to if you were to just do that, you would not compute the correct probability distribution. Okay, the resulting sampling distribution would not be consistent. Okay, and so, but there is a solution. What you would need simply to do is to reweight the samples by the probability of evidence given the parents. Okay, and so the algorithm that you would then obtain is called likelihood weighting. And so I will directly go over this function, which is about generating a sample. Okay, so for each, so again, you initialize some vector of n elements for n variables, and you initialize it with the evidence value. Okay, and then for each of the n variable in the network, if the variable is an evidence variable with some value xi in the evidence part, okay, no, let's say if xi is not one of the evidence variable, then what you do is that you just draw a random sample from the local conditional px given the parents, okay, and if it's on the other hand an evidence variable, okay, then you don't need to draw anything. You would just force this value to be equal to the value in the evidence, okay. But what you also do is that you will keep track of the probability of the evidence given the parents, okay, and you will keep track of this probability through a weight variable that you will then also return, okay. And that will give you the weight that you should attach to the variable, to the sample x that you've just generated. Okay. So now instead of summing ones in values of ones in some n vectors, what will accumulate are weights, this smaller case w, and will accumulate them in a new vector w. Where you have as many entries as the number of unique values x. Okay, and then again you would obtain now a vector of not counts but in a sense weighted counts. Okay, that you, if upon normalization, then would give you back the condition of x given e. Okay, so let's go back to this other Bayesian network with the 4 variables with cloudy, sprinkler, rain, and wet grass. And let's say we want to generate samples from the joint of this full joint distribution, but in which we have set the 2 variables, sprinkler and wet grass, to be positive. Okay, so if you follow the likelihood weighting algorithm, okay, you would first draw, again, following the topological order of the network, the C variable. Let's say it gives you a positive outcome. The weight variable would be equal to 1. Okay. Then you have to draw values for the variables sprinkler S and rain R. Okay, for the sprinkler, it's set by the evidence. Okay, so you don't want to draw anything, but you will remember this conditional probability of the evidence S given the parents. Okay, which is positive. So you multiply the current weight by this probability of local probability values. You draw some value for the other variable, the rain, let's say it's positive. And then finally, you access the fourth variable, which is set again by the evidence, so you don't have to draw a random value for it, but you have to keep track of its local conditional probability given the 2 parents, okay, which in this case would be 0.99. Okay, and so the weight for this sample would be given by this product of the local weights that you've collected for the evidence nodes, okay, and then will be equal to 0.099. Okay, so you would accumulate all these weights in these W vectors, and once you are done, once you've generated n samples, you just normalize them all to obtain P of W, P of X given E. So again, we can show that this algorithm is consistent. Okay. So first, the sampling probability that we use in likelihood weighting is given by this expression, is the product of the local probability values of the nodes given the values at the parents, but it's only over the non-evidence variables, okay? Because this is the only place where we are drawing, where we are generating values, okay? So the sampling probability of some variable, of some value x with evidence e, is given by this expression, okay? And the weight for a given sample x and e is given now by the product of the local probability values of the evidence value at the evidence nodes given their parents, okay? So again, with the same expression, except that now the local, it's only over the evidence variable, okay? So this is what you obtain in one or the other part of this if statement. Okay. That means the weighted sampling probability is given by the product of these two expressions. Okay. So the weighted sampling probability of some event x and e is given by these two products. Okay. And since in one we are multiplying over the non-evidence variable, and in the other one over the evidence variable. Okay, so there is no overlap between these things. So that means we are just now multiplying over all the variables in the problem, and that's give us again the same expression as the expression of a Bayesian network, which is itself equal to the joint probability of x and e. Now, given this, the estimated posterior probability would be computed. So p hat given x and e. So it will be proportional. So alpha means it's proportional to the number of times you've encountered x and e times the weight. Okay. So if you do not take into, if you make as if alpha was not there, okay, this expression would be equal to would approximate the joint probability value, okay, the joint of x and e, okay. And the alpha is basically in this case just the normalization constant, which is then giving you the conditional of x given e, okay. Now, so with this, yeah, as we increase the number of n of samples, okay, these weighted counts will tend to the actual sampling probability values. Okay, so this is why this expression is approximately equal to the true sampling probability. Okay. Again, with respect, and this is proportional to this conditional with respect to some factor alpha, alpha prime in this case. Okay. This is strictly equal now to the joint probability of x and e, okay, and this alpha prime corresponds to the normalization constant, and therefore we have the equality with the conditional of interest px given e, okay, and therefore again likelihood weighting would return consistent estimates. And so this is nice because now we are sampling, we are generating samples and we do that by also taking into account the evidence values. Okay, while before with rejection sampling we were not taking into account the value of E to sample. Here we take them into account. So this is helpful. The evidence is taken into account to generate sample. So that means more samples will reflect the state of the world suggested by the evidence. That's fine. But that does not solve, again, all of our problems, because the evidence, and this is the major issue, the evidence will only influence the choice of the downstream variables, but not the upstream variables. So if the evidence, if you look at the Bayesian, at some Bayesian network, and the evidence variables are only concern terminal variables, okay, they will never be taken into account when you generate samples. Okay, it's only if they would have appeared above in the hierarchy that then they would have helped in generating good samples. Because, for example, when we draw this first one, the cloudy, we draw a variable, a value, without taking into account the fact that, okay, we want S and W to be true. And this is precisely the reason why we have to reweight the sample that we generate. Okay. So we can use another strategy to solve this same problem, which is known as another family of inference by Markov chain simulation. So Markov chain Monte Carlo algorithms, or MCMC algorithms, are basically a family of sampling algorithms that generate samples through a Markov chain. So Markov chain is something we'll see next week. You just have to imagine that you maintain some, you're basically sampling values in sequence, and the sequence is called a chain, and we'll do that, and the chain can be of any size, can be infinite, and we'll just keep doing that, and to transition from one state in this chain to the next, then we just have to sample from a simple conditional probability distribution, which depends on the current, which only depends on the current state. Okay. Then this algorithm will generate a sequence of samples by basically making random changes to a preceding samples, or to the current samples, instead of generating each sample from scratch. Okay. So one way you could picture that is that you will have your Bayesian network, and there will be the variables of this network will be instantiated with some values, okay, and the combination of this value correspond to the state, okay, and then so that corresponds to a sample from the distribution that we want to sample from, and then we'll generate a next sample by not recreating a sample from scratch, but by basically transitioning from the current state to the next, okay, to a next, which will usually be done by simply making some small changes to the current state to generate a new state, okay. So there are several variants of this algorithm. Metropolis hasting is one of the most common MCMC methods, and the algorithm that we'll see just now is called Gibbs sampling, and it's a special case of Metropolis hasting. Okay, so it goes as follows. So we would start with some arbitrary instance, lowercase x1 to lowercase xn, which is consistent with the evidence. Okay, so again, what we want to do is to sample from px given e. Okay, and so what we would do, starting from this state, from this instance, would be to select one of the variable, okay, which is not an evidence variable, and we would resample its value, condition on all the current orders, okay, and of course with the evidence fixed, okay, and we would resample this single variable. We would then obtain now a new value for it, and this new value, together with all the previous value, would correspond to a new sample from our distribution, okay, and you would keep repeating that for long enough. And what you can show also is that you would under some conditions, under some assumptions, this would effectively lead to samples from the correct posterior distribution. Okay. So in this inner loop, this is the same procedure. So for each variable z, so z are the non-evidence variable, okay? That includes the query and the hidden variables. So for each of them in sequence, what you would do is that you would set the value of zi in x by resampling from the local distribution p of zi given all the others. So this conditioning mb of zi is something which is known as the Markov blanket of the variable zi. It's not too important for this course. You could just assume that we resample zi given the values of all the other variables. Okay. But the thing is, since we assume a Bayesian network, you don't need to condition on all the other variables. You can only look at a subset of them, and this subset is called the Markov blanket. It's basically the set of parents, the set of direct descendant, and the parent of this descendants, if I'm not mistaken. Okay, and then again we would collect samples x. We would fill in the bins of our histogram, and then finally would normalize the counts. And so this is nice because now with this algorithm we would be sampling the variables. So both upstream and downstream variables, while taking into account the evidence. Okay, because you do that not using the local probability distribution that you have at the nodes, but using this guy. Okay, and so this is strictly better than likelihood weighting, because in likelihood weighting you would only condition on upstream evidence, and you would never take into account the downstream evidence when sampling. So again, I can show you how it would go, for example, for the same problem with the 4 variables C, S, R, and W. And let's say we would like to draw from the posterior P of CSW condition on R being positive. Okay, so you would fix the evidence. You would randomly initialize all the other variables, and then what you would do is that you would repeat this procedure. You would pick any of the non-evidence variable, so either C, S, and W, and then we would resample Px given all the others. So for example, we would like, for example, to resample S given all the others, given C, R, and W. Okay, and that would give us a value at random, let's say positive, and that would be the next state in the chain. And then we would proceed. I would pick another non-evidence variable, let's say C. We would resample its value, so we draw a value from PC given S, R, and W. And again, let's say it's positive. We would repeat that. Next, we would select the variable W, draw a value for this variable given all the others, and let's say it's negative again, and it would repeat over and over until we have generated sufficiently many samples. Okay, so to conclude, I will just show you some concrete Python code which implement this. In the case of a simple multivariate normal distribution, so Gaussian distribution with several, not over one variable, but over n variables. So this is something we'll see next week, but let's just assume that, okay, what we'll try to do is to re-implement the procedure which is giving you random samples from a multivariate normal. Okay, so multivariate normal is defined. It's a distribution over continuous variables, okay, over vectors, continuous vectors, and it's described by two parameters. The first one is mu. It's a vector. It's so it's the mean, okay, but it's a vector of values, and sigma, which is a covariance matrix, which is a matrix of size d by d, where d is the number of is the size is the dimension of x. Okay. Then the probability density of px of this vector is given by this expression. Fine. Okay. But I could just use, for example, this multivariate normal function given by this package from Python. Okay. And what I would do, for example, here, I would say that that mu is equal to 0, 0, and that the covariance matrix is as a diagonal made of 1, and the covariance between x1 and x2, we have only two variables, is 0.9. Okay. So I would define this, and then given this distribution, I could call this RVS function, which I can use to sample a certain number of values from the joint, okay, from the distribution. And let's say I just draw 1,000 different samples, okay. And what I would obtain there is now a list of 1,000 values, one for each of the samples that I've generated, okay? And I could just plot these values, okay? So each dot would correspond to one of these 1,000 points that I've generated. And you see that indeed, if you compare that to the contours of the multivariate normals, the function seems to work properly and to generate samples that are consistent with the actual distribution. Okay, and we could verify that, for example, by computing the empirical mean. Okay, so we set the distribution to have a mean value of 0, 0, and the empirical mean is 0.01, 0.01. So we are not too far from the truth. If we increase the number of samples, let's say 10,000. If this is indeed consistent, we should get closer and closer to the truth. Okay, we get this, and indeed now we get values for our estimates of the mean is even better, even closer to 0, 0. Similarly, we could try to compute empirically the covariance matrix, and again we are not too far from the nominal values that we have set, which was diagonal with 1 once, and then the covariance term, which was equal to 0.9. Okay, this one. Now the question, the thing that I want to show you with this notebook is basically, this function. So how could we write a piece of code that actually re-implement this sampling procedure? Okay, and the way you could do that would be to use GIP sampling, as we've just seen. Okay, this algorithm, by the way, works both for discrete and continuous, variables. Could even mix them if you want. The only thing that we need in GIP sampling is to know how to draw from each variable given all the others. Okay. So in the case of multivariate normal, what we would need to define is how to sample from the first given the second, and how to sample from the second given the first. Okay. But from the properties of the normal distribution, okay, it can be shown that these two conditionals are themselves normal distributions, but now over only one single variable, okay, of this parameter mu and this covariance or this variance given by these expressions. Okay, so let's just assume that we have access to that and we know that, okay? And we do know how to sample from a univariate normal distribution. What we do not know is how to sample from a multivariate normal distribution. Okay, so we could just implement the Gibbs sampling procedure, okay? And what I would do is that would start with some random initialization of the state of the network, the Bayesian network, or some random vector x and 0, with the value minus 2.5 for x1 and of plus 1.04 for x2, okay? Then I could just repeat this loop, okay? So I would just iterate for 1000 iterations. And at each iteration, I would either resample x1 or x2, okay? And I would just simply, to do that, I would look if x is even or if j is even or not. I would either resample x1 given x2 or I would resample x2 given x1, okay? If I want to resample x1 given x2, okay, I know to do that, okay, I could just redefine the normal distribution of x1 given some particular value of x2, okay, which is given by this, okay. And to do that, I assume that I have access to a sampler for the univariate normal, and from the sampler, I generate one single value, okay, which will be the new value that I set for x1. Okay, and vice versa for x2, I would define the condition of x2 given x1 as this normal distribution given by this expression, and I would resample a single value that I would assign to x2. Okay, and then I would add the new version, the samples that I've just generated into my list of samples. Okay, and then I would return. So I would do this, boom. I would obtain again some list of values with 1000 of them. And what I could show you now is how the algorithm would draw these values, okay, as Gibbs sampling is run. Just take some time. It's not because the algorithm is slow. The algorithm has already finished there. It's taking some time just to build the animation. That you will see in a few seconds. Boom, boom, boom. Okay, here it goes. So what you see is Gibbs sampling running, and Gibbs sampling generating samples from this multivariate normal distribution. You see that every iteration I'm resampling either x1 or x2, the other one being remaining the same. And it seems to indeed to work properly. The sample that generate seems to follow the density, the actual density of this 2D normal distribution. So we could look at again at the empirical mean that we obtain from the samples that we've generated. You see that okay, it's not as good as we had before. It's not too far off, but it's not yet exactly equal to 0, 0. Okay, and in terms of the covariance, the diagonal is not that bad either, but it's not. I mean, the error is larger than the error that we had before with the SciPy implementation. So there is a reason for that. The reason is that the samples are correlated, and maybe also we have not drawn sufficiently many samples. So we could repeat the same, let's say, to sample now from this multivariate normal, okay, which is much more narrow, okay, and I would just do that by increasing the covariance between the two variables, okay. I could restart my sampling algorithm, run Gibbs sampling again. Okay, I would obtain this sample, and let's wait for the new animation to appear. It's taking some time. Should have reduced the number of samples. Okay, so here we go. It does not seem to work that well anymore, which is strange because the algorithm has remained the same. The only thing that we change is the distribution that we want to sample from. And the reason is that when we make this local change, when we make the transition from a state to the next, okay, we are using this distribution here, okay, but that means the sample that we'll get next is of course highly dependent on the current value of the state, okay. And in our case, for this narrow normal distribution, let's say you are here in the middle currently, a transition, let's say x1 is fixed and you want to obtain a new value of x2, then the range of value of x2, of course, is just limited to this very narrow region. So it will never happen that you make big changes, so you make big transitions from one x to the next, okay? And so this is, in terms of the value there, okay, you see that we are very far off now from the ground truth, which was 0, 0, and the same for the covariance. And the reason is that we are not sampling, we are not generating samples that are independent anymore, okay? Because to generate the next, we depend on what's the current state, okay? And so, for example, if you just plot the values of the x that we generate, you see that they are highly dependent between one another, okay? If they were fully independent, you should just see random noise in between so what is x? So this is for x1, so over the domain, so in between -3 and 3, okay? But from one sample to the next, it takes some time to arrive to another region in the space, okay? So just to convince you of that, let's say now I just say there is no correlation anymore. So the covariance term is equal to 0. Would draw from this, okay? Easy. We would run Gibbs sampling again. I will not generate this. Okay, now you see that the error is much better. The same for the covariance, it's close to 1, 1. I mean, we could improve by sampling more by generating more samples, but the covariance term also is close to 0. And more interestingly, this is what you would obtain. And you see that the correlation between a sample and the next is reduced a lot, okay, and that will help with the convergence. Okay, so this algorithm is nice. You can use both. You can use the evidence to sample both upstream and downstream variables, which is better than the likelihood weighting. But it comes, to be honest, also with some other problems, like the one I've just shown you. But still, there are with some assumption, you can show that this sampling process, the Gibbs sampling algorithm, will basically settle in a dynamic equilibrium in which the long-run fraction of time spent in each state is actually exactly proportional to its posterior probability. Okay, so we can show mathematically that the equilibrium distribution corresponds to the posterior probability distribution that you care about. Okay, and if you're curious about that, but this is out of the scope of the course, you can read this section from this textbook where you will find the demonstration. All right, so now it's time to summarize for today. So we have seen how to perform inference, and we've seen two families of methods, exact and approximate inference algorithms. For exact inference, the algorithm that you should remember is variable elimination. Unfortunately, this algorithm, the worst case complexity of this algorithm remains exponential in the number of variables. And we can even show that exact inference is NP complete, meaning there is no known efficient algorithm to solve this problem. On the other hand, we have seen approximate inference algorithm, which give reasonable estimate of the true posterior probability that we want to compute. And by doing so, we are able to cope with much larger networks than what you can do with exact algorithms. We've seen prior sampling, reduction sampling, likelihood weighting, and Gibbs sampling. Likelihood weighting will do poorly when there are lots of evidence. Usually likelihood weighting and Gibbs sampling will be insensitive to the topology, which is nice. However, conversions can be slow when the probabilities that you want to compute are close to 1 or 0. Okay. But what is nice with this algorithm is that they can handle arbitrary combinations of discrete and continuous variables. Okay. And that's it for today.